And then we'll do function stuff. All right, so there's several parts of lines. So some of this is just words I'm going to put because you know what they are. There's no reason to put vocabulary, like definition for you. All right, so graph of a line consists of x and y values. Okay, one way to write them is like that with a table, called your table of values. Okay, and when you have the equation of a line, each one of these is actually a solution point. A solution to that line. Okay, and that solution point consists of an input and an output, right? Input being x, output being y. Okay? Now those also have names. Well, not really names, but the input is the independent part of your line. The input is your independent variable of your equation. Okay, and once you put your x in, you can figure out what your y is. So that's your dependent variable. Okay, so while we're talking about x and y also, let's also talk about what is the x values to any graph. Domain or range. Domain. So this is also the domain of a graph. I know we're talking about lines, but it's lines and all other graphs. Okay, so then y is your what? Range. I feel like I have all this vocabulary to cover. I'm going to be everywhere with it. All right, so for our second one, we have domain and range. Remember, there's two types of ways to write that. There's your set notation, and then there's your interval notation. And I'll do an example with a line. Remember, your line just basically goes on forever in both directions. So set notation would be for x such that it's between the infinities. Oops, I forgot my negative. So that's what your set notation looks like, from negative infinity to positive infinity. No equal signs because you can't equal infinity. And of course, for a line, it would be the same for your y's. So you guys remember seeing set notation before? Now, as we moved up in the math world, it's kind of looks like it's gone to a lot of interval notation. So for the same line, or any line really, that would be your domain and be your range. Now, parentheses meaning it's not equal to. If I had an equal to, I would use a bracket. Okay, so got a couple of things done there. Any questions about any of that vocab so far? All right. Now back to some lines. We have, well, when I say lines, it's in your line chapter in there, but it does pertain to other stuff too. So intercepts, you got your x-intercept and your y-intercept. What does that mean to intercept? What's it doing? The x would be where it's crossing the x-axis, y where it's crossing the y-axis, where it's touching it basically, right? So this one will be, because if it's touching my y, it would be at a 0 and then something. And then this one would be the other way as an ordered pair, something and then 0. Now, why do we use those in lines? Basically because it has 0, and doing stuff with 0 is easy, isn't it? Okay. And then, we'll talk about that later. And then we have one more vocabulary. Now, your vocabulary in your book said point of intersection is what they called it. But what it really is a solution point for the set of graphs. So like it's a system of equations. And it's the solution point. So if it's, if we're in XY, then it's just a ordered pair. If we get into X, Y, Z, where we have 3D, it's a ordered triple. All right, so none of that's new, none of this is new. All right, anything I go over, I'm just writing down your vocab. Any questions though? All right, good. Can I erase it? Anybody still writing? Okay, let's move on to slope and equation of lines. So what's your slope? I can't hear.
Y equals mx plus b.
That's slope intercept form. What about slope? Yeah. Okay, so we got a few things with slope, but that slope intercept form, that's what I'm going to ask for next. First, what letter is slope? M. Rise over run. How else do you guys know it?
Y over x.
I need a little more than y over x. Just a little more.
Should I do y over symbol?
Right, and what's the change of symbol?
The triangle.
The triangle, which is called delta. Okay. So sometimes your teacher in college will be like, delta y over delta x. Okay, which means change of y over change of x. Now, what is that? What's the formula you learned in like 9th grade? That, right? These are all the same thing. But in terms of calculus, we're going to do change of y over change of x. Delta y over delta x.
It's fancy.
It's fancy, it's short, it gives you symbols. Yep. Well, like in college, you'd do proofs and the whole thing would be symbols and it'd be like a whole sentence. Because you know, proofs are sentences after you get out of geometry. And it'd be just all symbols. And like, when you're done, you're like, that's pretty cool. I just did a whole sentence in symbols. Okay, so next though is y equals mx plus b. What is that called? Slope-intercept form. Okay, so, which m, that's slope. So b, y-intercept. xy is just the ordered pairs, the solution points for that line. Okay. Did I end up doing, I quit at some point, I don't know if it was with you guys or not, doing point slope form? Have you seen that?
We've seen it, but I can't remember it.
Did you see it in Kim's class or mine? I stopped at some point, so I'm like, no, it was
I think
yours.
I thought it was hers. I thought it was hers.
Mine? Okay, then yes, it was mine, good. Then I quit the next year. Because what it is you can really put in a slope and a point, figure out what B is and do the same thing. But I'm still gonna put it up here. I think I still show my honors class, but I don't like make them, I just say memorize that one. Okay, you got your point is x1, y1, your slope, and then you end up usually rearranging it to look like this anyways. So, either way though. Alright, so got that. Then we have a couple vocab differences. Which when I was reading it, I thought it was interchangeable, but I guess it's not. Ratio versus rate. There's things you don't pay attention to when you're just a student. What it is ratio has the same units on top and bottom if we're talking about units. Okay, so for example, you would have something seconds over something seconds. So it's just a ratio of seconds. Okay, but over here, you would have a different on the top and bottom, so it'd be like centimeters per second. And that makes it a rate. Isn't that cool? Didn't know. I thought they were interchangeable. But what that gets us to is an average rate of change for our mathematical models. Okay, and what that is how does it change? The average, how does it change over time from interval to interval? And then mathematical models are your applications of anything we do, not just lines, but everything, which we'll end up doing a lot of with calculus. There's really not a whole lot of like application, but they'll try to pull it into real world situations. Okay. Any questions there? Oh, I forgot to put one more form. We have standard form. I'm going to go over here real quick. So standard form. I don't know if you guys remember from my class. Is that where we have some rules like A and B can't be a fraction, A can't be negative. Okay, they didn't have standard form in your vocabulary, but they have what's called general form, which is essentially the same thing except it's set to 0. And usually what happens is you got one or the other and they ask you to make it look like this. Sometimes they take this and ask you to make it look like that. So really when you guys are doing this work today, it's really going to be just, can you rearrange formulas? And yes, you guys can. That's how you are in this class. Okay, last thing about lines, and then we're moving on to functions. Parallel lines and perpendicular lines. What do you guys remember about those?
Parallel lines have the same slope.
Mm-hmm. That's really about all you need to know.
Perpendicular make a 90-degree angle.
Makes a 90-degree angle. Is a perpendicular, right?
Yeah.
And then these have the same slope because what's the definition of parallel lines? Two lines that will never intersect, right? And the only way for that is if they have the same slope. So what about perpendicular lines with this 90-degree angle? Yeah, flipped and opposite, so the fancy way is opposite reciprocal. Opposite and reciprocal. Or change the sign and flip fraction. If it's just like 5, how do you flip 5? It's not a fraction, is it? Of course it's a fraction. It's 5 over 1. We just don't write the over 1. So it's 1 over 5. Okay. Any questions about this? So at any point, so I'm going to give you a couple of problems to do. I'm not doing any examples. I'm going to make it super easy. You guys, can you do that? Any questions about this vocabulary? So where you think you could do a problem? Sketch the graph, find the intercept. We're going to talk about some transformations in a minute, but what other thing? So find intercepts, that's all it says. Sketch, graph, and at one point, what do we have? Perpendicular lines and parallel lines. Find the equation of the line, and they give you stuff. You guys good with that, you think? So I mean, that's what you should be doing at home. Alright. Alright, next part. Start functions. We'll see. We probably have time to at least get started. See if you have any extra questions. Are you going to do it again tomorrow? Probably not, because I'm getting it all done today, I think. And because I'm doing all the vocabulary, I'm going to stand up here and talk as long as I can about all the vocabulary and stuff. Maybe do some practice problems if I have extra time, of a couple things with functions. And then, but you guys feel free to email, remind, Google Classroom. I'll try to get to you as soon as I can. Basically, it's as soon as I pick up my phone. It's the next thing. Okay. Let's start with a relation. Do you guys know what a relation is? It's a set of ordered pairs. Okay, so this is a relation. relation. And that's a relation. And that's a relation. So all those are relations. Okay, we got our table of values. These are all order pairs. We have our bubbles over here. They're called something. I don't remember. And each one of these is an order pair, right? So 2, 5, 2, 8, 3, 6, 4, 7. So those are order pairs. This is in set notation. Okay, those are all lists of ordered pairs. And then a graph is a bunch of ordered pairs as well. So many that you can't just list them. How many ordered pairs is on that line? Infinitely many. Right there in that section, how many ordered pairs are there? Infinitely many. Okay? So, way too many to write. Okay? So, any question about our relation? We got graphs, lists, this thing, table. Alright. So, why I did that is because we need to show that you can be a relation and you can be a function. You can be a relation and you cannot be a function. So, there is differences there. Does anybody remember what it takes to be a function? Vertical line test when we have a graph. But what if I don't have a graph? I guess you can make a graph. There's really only thing. No x's repeat. Okay? There's only one x for the many y's. Alright, so you know all of those are relations now. Is my table a function? Yes, it is. They all have different x's. What about this thing? No, y, what repeats? The 2's. What about this one? No, because 2, 2, and 2. And then what about this one? Does this pass the vertical line test? Okay. Okay. All right, so we have a relation, relations that are functions, relations not functions. Now that we have our functions, we have another step into it, okay? It's called one-to-one function. And this is y's don't repeat. Of course, this is all after I know it's a function. Okay, so I've already done the vertical line test. I've already checked to see that x's don't repeat. Then I go to one-to-one. So that the y's don't repeat. So the fancy way to say this is for every x there is one y. For every one x there is one y. Only. Okay, so would this be a one-to-one? Yes. Does any of these repeat? No. So this would be a one-to-one function. So it's a relation, it's a function, and it's one-to-one. Okay? This one isn't even a function, so I don't even have to worry about if it's one-to-one. Same here. Okay? Now here, people like to say there's no vertical line tests, but or horizontal line test, but there is. The horizontal line test. And that tests functions for one-to-one. Okay? So once again, now that I know its function, I can see if it's one-to-one. Would this pass the horizontal line test? It works the same way as the vertical line test, except it's horizontal. And yes, it does. There's no place that it comes back. So let's look at a quick one. So like your parabola, your quadratic. Okay, that is a function. It passes the vertical line test, but when I go to do the horizontal line test, it does not pass. So this is not one-to-one, not a one-to-one function. Okay, a big reason one-to-one is important for us is that when it comes to inverse functions, we can only find the inverse of something that is one-to-one. Okay, all right, and you got one more vocabulary word. For me, it was a little hard to grasp, but it's onto. So when something is onto, it means it's a relation, it's a function, it's one-to-one. And then after you say, is it one-to-one and onto or one-to-one and not onto? What it means is the range is infinity. Goes from infinity to infinity. Infinite. Okay, so this was one-to-one. Would this be considered onto? No, because this is my only list. Is that infinitely many? No. Over here though, this is one-to-one, but my range goes in both directions forever. So this would be considered onto, because it's infinite. All right, so for functions, we have independent and dependent variable as well, domain and range, we already talked about that. Talked about one-to-one vertical line test. Okay. All right, we're getting through this. Okay, any questions on those? That basic vocabulary of functions. All right, so next though, let's talk about like function notation. All right, so for our function notation, remember it takes our dependent variable, y, and changes it to f of x, and names it, or g of x, or h of x, or whatever way you name it. All right, so you take your basic XY graph, talking about x and y, and it changes to x and then f of x. Okay, so it is also supposed to be labeled f of x and not y. Okay, x still being your independent variable, f of x being your dependent variable. Okay, but what this does, it also helps us with that. Okay, so it tells us what we can replace our independent variable with. Okay, so it has a lot of things. So what I'm talking about is evaluate. Okay, so remember if I have f of 2 equals 2x plus 1, that's not actually right, so let's put an x here first. And then I say, what's f of 2? What does that mean? What did I just do? I replaced x with what? 2. So what do I do to the function? Replace x with 2. So f of 2 is, what's that, 5? Okay, what if I say, replace it with x minus 3? Okay, if I say f of x minus 3 for this function, I'm going to do exactly what I just did with 2. What did I just do with 2? Plug it in. Plug it in everywhere I have x. It becomes x minus 3. Okay, so then my answer ends up being a expression. Okay? Any questions doing that? Anybody else to do that? Okay, good. I'm gonna skip this stuff for a minute while I'm talking about functions. Alright, so evaluating. Now you're also going to be doing other function operations, which I need to get you a worksheet of that. Okay, so first one is function addition. This is what it looks like. F plus g of x. What that means is take your f of x and your g of x and add it together. So, I'll do some examples. Let's see. Alright, so I have f of x here and g of x. So when I do f plus g of x, that means take f of x, 6x squared, and add g of x, 2x. And then that's it. And you do it in the order it tells you. That's not so important when it comes to your addition or your multiplication because it's commutative, but your subtraction, it does matter. So if I said g plus f of x, not plus, we just do plus, minus, that would mean you'd have to take g of x first, minus f of x. So it's telling you exactly what to do. All right, multiplication. Now, if you're able on these to combine like terms or anything, of course do that. You can't. But this one, multiplication, I was able to go further, simplifying. So I have 12x cubed. Okay, division. Of course, also has to be done in the order they tell you to do it in. Over 2x, and that makes what, 3x. So simplify if you can. Alright, and then the last function operation is composition. Do you guys remember composition? Yes? No? Yeah. You're taking a function, putting it in a function. Yeah. Good. And it gets the symbol of a little open circle. Okay, and it's also done in order from left to right. So when I write this, I'm going to say f of g of x. So what I have now, what is awful writing? What I have now is an evaluating function. So it's saying evaluate f at g of x. Okay, so first, what is g of x? It's 2x. So I can replace g of x with what its equivalence is, which is 2x. Now what this is saying is evaluate f at 2x. And we just did an example similar. So now I say 6 is 2x squared. Sorry. This whole thing is f of g of x. Which is, what's that, 4x squared, so 24x squared. Is the final answer? Okay, and they can do that multiple times. You know, f of g of h, f of g of g, f of f of f of f of f. They can do it whatever way they want to do it. And it just means keep taking it, put it in, and every time you do it, you start from the center and work your way out. Okay? That's composition. All right, composition. So we just composed, this fancy way of saying, I just composed f of g. All right. Got a big chunk done right there. Okay, now we got just some more vocabulary. Any questions with those? Because I have a worksheet of that stuff for you. That's because they didn't put good examples in your book. And then, by the way, all of this stuff so far I can do on CUDA, so there's no issue with tests so far. I'm still having you work out of your book, but I can do stuff on there. So we can retake tests. Okay. Let's look at a couple more examples of stuff. Where do I want to start? Let's just talk about transformations first. Okay, so since we were just talking about here, and I have a tape. Since I was just talking about that function stuff, what you can see happening is transformations as we do this. Okay? So there's a table. I'll write the table. That basically is a good explanation. None of this stuff is stuff you haven't done before. It's just now written in one place. So we have our original function, which is I don't like how they have this. It's weird. I'm not going to write how they wrote it. We're just going to say original function f of x equals whatever. Okay? So, what you can tell with transformations just right off, what's happening, is if we move left or right, okay, in my class, we talk about the transformation equation that I talk about. So you guys know I've seen that here, but anyways, let me finish up. Okay, so left is opposite of what we think. It's x plus c, and right is x minus c. It's just being written different. So this is the left and this is the right. Okay, the up or down is going to be the function plus, I didn't see again, but we'll say plus c. I'll do that part like they were. So that would be your up and that would be your down. Alright, and the last thing, like in my transformation, was the flip. So if you guys remember A, if A was negative, it flipped. So that's the same thing here. So the flip, okay, but we're going to start calling it, because I have to remember you guys are smarter than my regular class. So reflection across x-axis. You know, because I got to dumb things down sometimes. And that's whenever your function is negative, out front of the function. Now, not in my class, but probably in Math 2, you guys talk about reflections across the y-axis, reflections about the origin, should have been on one of those worksheets, you guys.
Like, we got that. And also, we didn't find out how far away the guy is from the house.
They've seen one thing like that.
So what you're going to do here is, remember we just talked about evaluate. So that being a negative x inside to get a reflection across the y-axis, what does that mean my function would do? What would we do to my x's in the function? They would all get a negative. Good. That will reflect us across the y-axis. And then to do it about the origin, I'm sorry, so much vocabulary, but good. At least it's worth something. Is when you do both x and y, gets the reflection. And then it gets, so if it's over here in the quadrant 3, then it gets reflected back up into quadrant 1. So that's what it means to like reflect about the origin. So the center is the origin that reflects around it. Okay, so that's your transformations. For all graphs. All functions, I should say all graphs, excuse me. All functions. Okay? Alright, and then one more just kind of vague vocabulary I need to talk about. Is all these functions we're talking about are called elementary functions that are broken into a couple different pieces. So algebraic functions is basically most functions you do. Okay? okay? What other functions do you guys know? Trig functions? That's another one. And then one more that we really don't hit a whole lot, but I know you've done, because I've done it, and then I know, I don't know if it's spelled right. I can't even say it, so. We've done in my class, Math 3, I'm sure you guys did last year, is your exponential functions and your logarithmic functions. We don't really do that a whole lot all the time, but when we start getting into calculus, we are going to like our exponential and logarithm, because it makes stuff a lot easier. Okay. So, algebraic functions consist of polynomials, radicals, and rationals. Okay, I'm going to go ahead and write it. Okay, trig is your trig stuff, sine, cosine, tangent, cosecant, secant, cone, tangent. Exponentials, you guys know that's whatever base raised to an x power. Logarithms, you basically switch it around, the inverse. Okay, now why I wanted to kind of go over that real quick is because there's a word you're going to hear pretty often, and it's called transcendental in calculus. If I can remember to say it anyways. Okay, and what those are is basically non-algebraic. So that's these two. Trigonometric, exponential and logarithmic are the transcendental functions. Now once again, the reason why you hear that a lot is because those are the ones when we get into calculus are easier to deal with than the algebraic. Okay? I think I got all my stuff. There's implicit and explicit, but that's not big deal. Composition. Oh, one more. Even and odd graphs. I'm going to put that over with the transformation. Alright, this vocabulary is used a lot. I don't know why. I don't use it a lot, but it does. It shows up in stuff over and over and over again. I'm sure we'll figure out why at one point. But basically what an even graph is when you have an even exponent, okay? When negative goes in, what happens to the x basically value whenever it goes in, like a square? Right? What's -1 squared? +1, right? So that's what it means by this negative x becomes a positive x. Okay? So that's your squares, your 4th roots, 6th roots. Those are your even graphs. Okay, and then your odd graphs are your odd exponents. Basically, when you put in a negative, it comes back out a negative. So what's negative to the third power? -1 to the third power? -1. So that's kind of what that means. And that's the last of it. Yay, we got through it, and with a little extra time. Okay, now I'm going to put the homework up here. It looks like a lot, but remember, it's super easy. Remember that. What I think so.
You remember when Hard gave us a worksheet on even monographs? They didn't teach it, he just gave us worksheets and here do this.
mean, some of these are like, you're just gonna look at it, it's like, does this pass the vertical line test? Okay, so just remember, comment.
You know, you saying that is making me think it's gonna be like 200 problems.
It's not that new.
Eight.
I know, I kept waiting for like 4.
I know that kind of makes me.
I hated eight.
This could be long. Let's get a picture of that.
Let me see if I meant odd on this. I probably did. Oh, yes, that's odd. Alright, so that's odd there. Is that 4 or 5, 6, 7, 8? No, I'm not. That's why I gave you the warning. And I have a worksheet. Thanks, Amy. Thanks.